Hi, this podcast deals with the back of your fall review, back of 1A. It goes into naming compounds, moles, percent composition, and empirical molecular formula. So let's take a brief look at naming some compounds. So if you look, you have your periodic table, and this line here separates the metals from the nonmetals. It's dividing line, right? That's the semi-metals that live on that line. And so if you look where lead lives, lead is a metal. It lives under those stairs though, and so therefore it's in Rome, right? And so it has a Roman numeral. So when you're writing this, you would go ahead and make sure that you would write lead. I don't know yet, Roman numeral. And then you look at this and you say, oh, that's a polyatomic ion, and that is phosphate. So that's step one to naming this compound. Step two to naming this compound is trying to figure out what in the world the charge is on lead. Well, you know for a fact that the charge on phosphate is -3. So phosphate is -3. Cover this whole mess up right here and say -3 times 2 is -6. So if that's -6, my whole positive side has to be +6 as well to balance it out and make a neutral compound. So what times 3 gives you 6? +2. That 2 is what goes right here. That's the Roman numeral. Now, how do you name NaF? Well, Na is a metal, isn't it? A cation. And Na is right here. It is not a Roman guy. It is in the +1 column. Okay? And so you don't even need to worry about charge here. The only time you need to worry about charge when you do metals is when you have a Roman guy. So sodium is a metal. And if it's a metal, it's a loser. It's a cation. You just go ahead and name it Mr., right? These were the misters, the metals, and the misses, the nonmetals or the non-males. So I'm going to name this sodium. And fluorine, but she changes her name to fluoride. And remember, you can remember how to spell that by saying fluorine, like you're from New Jersey, and it's fluoride. All right, how do I name these? Remember our staircase. That separates the metals from the nonmetals. This is Rome, remember? This whole area is Roman numerals. Okay? This area right here, oops, I have to change the color, is Greece. When in Greece, you speak Greek. Mono, di, tri, tetra, penta, and it goes on, but that's 1, 2, 3, 4, and 5. I need that because I have carbon, and where does carbon land? Looky there, it lands in Greece. That means you speak Greek. So you write down carbon, but instead of writing just carbon, I'm going to go ahead and write dicarbon because there's 2 of it. In Greece we're fancy and we talk about the number. We say, hey, there's dicarbon. How many is here? 1, so we call it monoxide, but instead of calling it monoxide, the syllables roll off your tongue better if you cross that O out and just call it monoxide. So that's when you use Greek prefixes. H2SO4 is an acid. We're not going to do acids as far as, or name them for this quiz test that we're doing. Okay, so this is sulfuric acid. We'll go into naming in a different podcast. But for your sake, you're going to call it hydrogen. Right, because that's what that's right there. And this is SO4, so that's sulfate. Because that is another way to name it. What's this one? Oh, look, it's an acid also because it begins with H. And so the acid for this, if you named it correctly, would be hydrofluoric acid. But again, for this assessment, for the fall review, we're not going to worry about acids. But you would be able to name it hydrogen fluoride. Okay? So let's look at this FeP. What is Fe? Fe, let me go ahead and get you scared of everything, okay? So I'll just write this here, it's easier, instead of me scratching in your brain. All right, so I have Fe. Where's Fe live? Oh, look, Fe's in Rome. It's a metal, right? Isn't it a metal? That means there's a thrower and a catcher. This throws and this catches. This is positive, this is negative. This is a metal, this is a non-metal. This is a cation. This is an anion. And together they make a neutral compound. So what is iron? Iron is iron, and I'm going to name it as a Mr. and a Mrs., but I don't know iron's charge. But I do know phosphorus is going to turn into phosphide. I do know phosphorus lives in the not -1, not -2, but the -3 column. And so therefore I know that phosphorus has a charge of -3. I'm going to change that to blue. My pen doesn't like to do that, does it? So if that's -3, and there's one of it, that means there's a total of -3. That means 1 times +3 is going to give you a neutral compound of absolutely 0, and so therefore I'm going to put iron Roman numeral 3 phosphide. That's how you name that compound. Now, how do you write the formulas? Well, you look on your periodic table. Magnesium's a metal. So magnesium's a thrower, it's +2. Hydroxide's a polyatomic ion. That whole clique or group has a charge of -1. Cover this mess up and just look at the +2 and -1. Throwing 2, catching 1, how are you going to balance it out? You need 2 of these, don't you? So therefore you need to put this in parentheses since the polyatomic ion and put a 2 out here, and that balances your charge out. Calcium is a metal. So therefore I'm going to write calcium here. Calcium's charged +2. Sulfide on the periodic table has a charge of -2. So calcium and sulfur come together to make calcium sulfide, and that is balanced by itself because the +2 cancels out the -2 for a charge of 0 since it's a compound. Iron 3. Iron lives in Rome. That 3 is the charge. Oxide is oxygen. If you look on the periodic table, it has a charge of -2. How are they going to play ball? Fe throws 3 and oxygen can only catch 2. So therefore, you need to write Fe2O3. Because if you look at charges of +3 and -2, the total positive charge is +6, right? 3 times 2 is 6. And the total negative charge is -6. That balances out to equal 0. So this is your answer right here. All right, let's move to moles. All right, so you draw your mole map. I've got moles here, 1 mole in my mole hole. I've got grams in the periodic table, 22.4 liters, volume. This is things like molecules, formula units, atoms and ions. And the magic number is Avogadro's number 6.02 times 10 to the 23rd. So one of your questions on here is, what is Avogadro's number? It's the number that's in a mole. So what's a dozen? 12. How many particles are in a mole? 6.02 times 10 to the 23rd. And how many atoms are in 1 mole of any element? 6.02 times 10 to the 23rd. Does this number change? Only if you have half a mole or 2.5 moles or 1.2 moles. So for 1 mole, that's always consistent. Like I say a foot, you say 12 inches. I say a dozen, you say 12. So let's do this problem, all right? Now, how many atoms are in 1 mole of NaF? I am underlining this. I don't know atoms, so I write 1 mole of NaF. And I'm going to go ahead and say I do not want moles. I do want atoms. And what's true, in 1 mole, I pass by 6.02 times 10 to the 23rd. Remember, you can put this in parentheses if you want to. You don't have to, though, because it's on the bottom. All right? Now, when I do my math, I actually have just 6.02 times 10 to the 23rd atoms of NaF. Okay? Now, let's go to the next one. And no, I don't have a map, but I'll draw a partial one. Mass in grams, what am I doing? I'm going from moles back to grams for this. I have 1 mole here. I pass the periodic table and I'm going to grams. So, I know I have 2 moles of nitrogen. By the way, fix this on your worksheet because N is N2, right? Diatomic. Gen, UN, nitrogen, chlorine. Okay? So I'm going to go ahead and put words up here, right? Words up here. Go down here. I'm going to take moles and change it to grams. And in 1 mole on my mole hole, I'm going to look on the periodic table for N. And nitrogen is 14. I have 2 of them, so I'm going to have a total of 28. And that 28 goes right here. 2 times 28 is 56 grams of N2. All right. Now how am I going to do the next one? I have 3.01 times 10 to the 23rd atoms of chlorine. I want to go ahead and change that to grams. How am I going to do that? Well, I'm going to draw a mole map for you here. Get rid of this stuff. All right, and on my mole map, I'm down here. I'm on atoms. I need to pass 6.02 times 10 to the 23rd to go to 1 mole in the mole hole, and then go to grams and pass the periodic table. So I'm going to go ahead and say I have 3.01. Why would I recopy that, right? Let's go ahead and erase this and move it over. There you go. All right. Now, words up top, go down below. I have atoms of Cl2. And here I'm going to put 6.02 times 10 to the 23rd because I'm passing by that to go to my mole hole of Cl2. I do not want moles of Cl2. Right? I just did this, didn't I? In that first step. I do not want moles of Cl2. I want grams of Cl2. And here I'm going to go ahead and go over this way. So 1 mole of Cl2. On the periodic table in Cl2's box, I have 35.45 grams. But I have Cl2. So I'm going to multiply it by 2. And 35.45 and 35.45 is 70.9 grams of Cl2. When I do my math, and I need to put this in parentheses on the bottom, I come up with 35.45 grams of Cl2. Now, how do I find the number of moles from grams? Well, on my mole map, I'm on grams and I'm going to moles for this first problem. 1 mole in that mole hole, pass the periodic table. I underline my 12.15 grams. I do not want grams, so I write grams down here. I'm traveling from grams to moles, so I put the word mole up top. I'm on a mole map, I put the number 1. In Mg's box on the periodic table, I see 24.31 grams. When I do my math, 12.15 times 1 divided by 24.31, I get 0.499 moles of Mg. All right? Now how do I do this bottom one? This bottom, where am I on my map? I need to change it to moles, right? That's what my problem says. How many moles do I have? Well, I'm on atoms. And I need to go up to moles from atoms. 1 mole here. And I'm going to pass by 6.02 times 10 to the 23rd. So, words up top go where? Here. I do not want atoms. of fluorine. I want 1 mole of fluorine. Okay, so let me go ahead and erase this and get it out of the way. So what am I going to put down there, guys? Well, folks, I'm going to go ahead and put down 6.02 times 10 to the 23rd, because that is exactly what I pass by when I go from atoms to moles. Now what am I going to do? I'm not going to do my math, and I need to put this in parentheses. Have to. Okay, if you forget, just put everything in parentheses as far as scientific notation goes. Okay? Now when I do my math there, I come up with 0.249 moles of F2. Okay? And by the way, we need to change that because F2 is not F on your periodic table, it's F2. Okay? All right. Now, how many atoms are present in a 251.2 gram sample of manganese? Not magnesium, but manganese. And I'm going to have to do this one with you because I didn't do this ahead of time. I'm on grams, right? So I'm going from grams to moles. I'm going from moles down to atoms. So what am I going to do? Pass the periodic table and use 6.02 times 10 to the 23rd. So what do? You put grams down here of manganese, and I put 1 mole here. And 1 mole of manganese is 54.93. Do I want moles of manganese? I do not. I want to put the word mole down here. And I have 1 mole, and I'm going to pass by 6.02 times 10 to the 23rd moles of manganese. Sounds like I really like saying that word. And I'm going to go ahead and do my math. And if I do 251.2 divided by 54.93, and then multiply that by 6.02 times 10 to the 23rd, and again, you don't need to put this in parentheses, but if you have to remember one, if you always forget when to do it, just go ahead and do it. And I'm going to get 2.75. Now be careful because you need to look over on your calculator. If it ever says E, it does say E. So it says times 10 to the 21st. Fourth, I can talk. Atoms. I forgot to put that up here. There you go. Of manganese. Okay? All right, now, let's figure out the charge of tin in SnO2. Well, what is tin? Tin is under the stairs, isn't it, on the periodic table? So you would name this tin, I don't know yet, oxide. And since tin is a Roman metal, you're going to go ahead and say, I know oxygen's charge. Oxygen's charge minus 2. 2 times minus 2 is minus 4. So that means tin has to have an overall charge of 4. If there's 1 tin, that has to be positive 4. So if you were to name it, it would be IV here. But tin's charge is positive 4 in tin oxide. That takes us to percent composition. And I know I'm moving fast, but you can always wind it back or just freeze the screen and look at it, okay? This is meant to be a review, not a teaching session. So what's percent composition? That's the part by mass over the whole by mass times 100. So if you were to take this box and this circle, which is an apple or cherry, and this donut with sprinkles on it, and figure out what, if you had to mail it in a box at the post office, and you wanted to know how much this box was out of the whole thing, you'd have to take the mass of everything. The box, the cherry, and the donut, and that will go down here. All right, you add all those up, and then you'd figure out just the box, and the mass of just the box will go on top. And that will be part of the box over the whole, the box, the cherry, and the donut by mass. So now let's find the percent composition of sodium chloride. So you go ahead and write down part over the whole times 100. And I'm going to go ahead and I'm going to add up sodium chloride. Sodium is 22.99 grams. Chlorine is 35.45 grams. If I add those two together, I get 58.44 grams. I'm getting those off the periodic table. And I just found the gram formula mass. The word here can change, right? Gram molecular mass, gram atomic mass, or I can just call this the molar mass. The bottom line is, what am I finding? I am finding, so I'm changing my A's, so that's why I'm doing that. I am finding the molar mass. I'm finding the mass, period, end of story. Right now, why do I want to do that? Because if I find just the percent composition for sodium, I'm going to do 22.99, because that's the mass of sodium in grams, over 58.44, which is the mass of sodium chloride in grams, and multiply it by 100. If I don't multiply it by 100, I have a ratio, not a percentage, and that gives me 39.34%. Now I'm going to do chlorine. I'm going to do the same thing. Put chlorine's mass over NaCl. Now I don't make it Cl2 here because I'm talking about chlorine in the compound. So the mass of chlorine in my compound is 35.45 grams, and look, grams cancel, yeah? Over 58.44, the total, times 100, and I get 60.66 grams, or excuse me, 60.66%. And looky here, that adds up to equal 100, because that's what I have, 100% of my compound. Now let's do MgCl2. Mg has a mass of 24.31. I have two chlorines with 35.45 each. That equals 70.9. If I add up 70.9 and 24.31, I get a total mass of 95.21. Okay? So I'm going to do part. How much magnesium is in my magnesium chloride over the whole? How much chlorine is in my magnesium chloride? Now if you notice, this time I have two chlorines, don't I? So I need to include both of them. Here, I only had one of each. Here I have one magnesium, but two chlorines. So I'm going to take 24.31 for magnesium and put it over my total. This is my grams of MgCl2. I'm going to put it over my total, which is 95.21, and multiply that whole thing by 100. In doing so, I come up with 25.53%. That's my percent of magnesium in my magnesium chloride. Now how do I do this one? Do I take 35.45 or 70.9? I take 70.9 because that's the mass of two chlorines over 95.21. And again, that's a ratio, so to get a percent, I need to multiply by 100. And my answer to that is 74.47%. Okay? With me? Alrighty, guys. My next problem. What is an empirical formula and what's a molecular formula? An empirical formula is the simplest whole number ratio. And a molecular formula is the actual formula of a compound. So, let me show you this. H2O is water. Can you simplify that anymore? No, you can't. So water's empirical and molecular formula are the exact same. And that happens. What about C6H12O6? That's sugar. Or one of them. There's lots of oses, right? So glucose, fructose, all those things. Sucrose, that's a sugar. So what is the empirical formula for that? We'll look at that and say, hey, 6, 12, and 6 can be simplified to this, can't it? So this is the molecular formula, and this is the empirical formula. Let's go the other way. What if I have CH4? Is that an empirical formula? It sure is. So what is a possible molecular formula? Could CH4 be a molecular formula? Yes, it could, because they can be the same. Could C2H8 be a possible? Yes, it could, because you multiply C and H by 2. Could C3H12 be a possible? Yes, it could, because you multiply CH4 by 3. Could this be a possible? No, I say, because if you multiply carbon times 4, you get CH4. If you multiply hydrogen times 4, you get 16. So that is not a molecular formula that matches the empirical formula. So I expect you to go this way and this way. What's the poem for the empirical formula? Percent. We should make up a song for this. To grams, although some of you learn percent to mass. Grams or mass to moles. Okay, I'll write that down because some of you did memorize it that way. Divide by small and round till whole. All right, so remember that poem. Now let's do these. So our first problem, whoops, come on. Find the empirical formula for a compound with 63.52% iron and 36.48% sulfur. If I have 63.52% iron, I'm going to change that word percent to grams. Same thing here, 36.48 grams of sulfur. There's my percent to grams, or my percent to mass. Now I need to change each of these to moles. Didn't mean not look like a hook, almost looks like something from our SPDF stuff. So I'm going to put 1 mole here and put grams of iron down here because I want it to cancel. 1 mole here and grams of sulfur to cancel. And I look on the periodic table and the mass for iron is 55.85. Let me write that a little clearer for you. And the mass for sulfur is 32.06. Now when I do my math, in this case, I get 1.137 and 1.137. Okay? Now, what did I do? I went percent to grams, grams to moles, right? These are both moles. Divide by small. Well, guess what? These are already smallest. Number is the same. They're both the same. So I divide both of them by the smallest number, which just happens to be the same. And guess what? My formula is Fe1S1 because that's equal to 1 and that's equal to 1. If this had been equal to 2 for some reason, because of the way it divided out, then you would make this a 2 right here. But that's not the case. Okay? CH5 is the empirical formula. The formula mass, or the mass of the real formula, the molecular formula, is 85 grams per mole. Find the molecular formula. So CH5 is its simplest form. You want to find out what it really is. C what? What are these numbers down here? That's your job. Now, what do you know? You know the mass of what it really is 85 grams in 1 mole. So this is me. They always give you M. So they're going to say that the real mass is 85 grams per mole. You need to find the molecular mass. Well, how do you do that? How do you find the mass of CH5? You look on your periodic table and you say the mass of carbon is 12.01 and the mass of hydrogen is 5 times 1.01, and here you don't have to be as exact. So this is 12, and this is 5. That adds up to be 17. I put my 17 down here. So what I have, my empirical formula, is 17. It's lighter than what it really is. By how much? 5 times lighter. So that means you're going to take 5 times CH5, and you're going to get your real formula, which is C5H25. All you do is multiply here and multiply here, just like we've always done. I'm going to do one more because it's a combination kind of problem. And I'm sorry, but both these I picked are simple as far as the masses dividing. So I'll explain that in a second. So here I have a compound containing nitrogen and sulfur. And by mass, it has 69.6% sulfur. I know the molar mass of the real compound. What is the molecular formula? Well, first of all, I don't know the empirical formula, do I? So this is my me part right here. But I need to know my empirical formula. So how do I do that? Well, they give me 69.6% of sulfur. How do I figure out nitrogen? Well, you take the 69.6% sulfur and subtract it from 100. And when I do that, I'm going to go ahead and get 30.4% nitrogen. So now that I have these two right here, I'm going to go ahead and do my problem. So I'm going to take 69.96 grams of sulfur, right, percent to grams, and 30.4 grams of nitrogen. Change grams to moles. All right, and nitrogen's mass on the periodic table is 14, and sulfur is 32.06. When I do my math, I get 2.17 and 2.17. That's what I'm talking about. Usually these numbers are not the same, sorry. Okay, I just happened to pick two examples that had the same number. Usually they're different, and you have to pick the smallest number. That's the divide by small, right? Percent to grams, grams to moles, divide by small. Well, these are both the same. So I'm going to divide by the same number. Okay, so what's that mean? That means my S and my N are 1 to 1. That's my empirical formula. Now, how do I do my molecular formula? Well, I go ahead and use that M that they give me. What is that M they give me? They give me 184 grams in 1 mole. That's what really is in that one molecule. So I take that 184, I'm going to divide it by the mass of SN. So what's the mass of sulfur? 32.06. What's the mass of nitrogen? 14. And when I add that up, I get 48. Okay? 48.06 if you want to be exact. So what is 184 divided by 48.06? That gives me 3.8. That means that my real molecule is 3.8, or let's round that to 4, times heavier than this. So that means it's not SN, that means it's SN times 4 times heavier. So my formula is S4N4. And that, folks, is it.